So our second podcast in chapter 20 is going to be dedicated to entropy. We introduced a little bit of entropy in the first podcast, but here we're going to go a little bit more in depth, and we're actually going to see how we're going to calculate entropy and figure out what the units are for that and those sorts of things. Entropy is given the symbol of S. Again, I think that we just kind of run out of symbols when it comes to things in chemistry. So, you know what, we already have E for energy. Enthalpy is H, so entropy, they just gave the symbol of S. Not 100% sure why. All right, entropy is something that we call a state variable, and we've talked about state variables before. And a state variable just means that it's dependent upon the state of the system at that moment, not how we got there. Probably the best state variable that we talk about is temperature. I remember, the temperature, just like if it's 72 degrees, right, in your apartment or house or whatever right now, right, do you care what the temperature was, say, 24 hours ago? No, you only care what you feel like right then. Do you need to go and, put on a t-shirt? Do you need to go and put on a sweater or whatever it is, right? And you don't really care how you got there, right? All you care about is what the state is right then, what that temperature is right at that moment. That's what we mean by a state variable. Entropy is the same thing. It just is describing the state of our system right at that moment. Not how we got there, not what it's going to be like in the future or anything like that. As we talked about with our entropy, right? Entropy is an increase. As entropy increases, it's an increase in the randomness of our system or an increase in the disorder of our system, right? That's two things that mean the exact same thing, really, here in chemistry. All right, in chemistry, we talk about these things being in microstates of each other, which is different ways in which molecules can be distributed, right? So if we thought about, having a couple of mixed gases, right? Could, 90% of the gases be on one side of the room and 10% on the other side of the room? That's one microstate. Or maybe 80% is on one side of the room and 20% is on the other side of the room, and then they're mixed together. Those are what we mean by these microstates. There's different ways in which our molecules are distributed in the area in which they're distributed. We call those microstates. I will never say microstates again, right? Microstates will come up whenever you do physical chemistry if you take that course. But all we really care about with these things, which we're calling these microstates, is we're just talking about how many different possibilities do we have. Right? And so the more possibilities, right, the more ways that we could roll, say, a 7, there were 6 ways, right, or a 12, which there was only one way, right? That's what we mean by the microstates. All we care about the different number of ways that we can get to our answer. So whether something is really well ordered or whether it's disordered, right, leads us to whether something has a high entropy or a low entropy, right? A high entropy means that it's relatively disordered. A low entropy means that it's really well ordered. So here my example is I have a couple of beakers that are sitting up there with some marbles in them. So let's say that I gave you, right, a bag, right, and it was, say, like a black felt bag that you couldn't see through, and all you could do was reach your hand into the bag, and it was filled with some blue or some green and some red marbles, and then you drop them into a beaker. All right, and we shook up the bag, and you didn't know what you were going to get. You just dipped your hand in, grabbed a marble, and put it into the beaker. All right, do you think it's more likely that you're going to end up with a beaker that looks like the one on the left or the one on the right? Right? The odds of you pulling out all of the green marbles first without being able to see them, and then pulling out all of the red ones randomly like that too, right? The odds of that are so tiny. But the odds of you pulling out a random array of greens and reds and it looking like the beaker on the left, that is much more likely for it to happen. All right, and so the more disordered something is, the much more likely it is. So the much more likely something is, another way of saying this is that the much more likely something is, the more random it is, or the higher the entropy of that state is. All right, and the t-shirt there says entropy isn't what it used to be, just meaning that the universe is always having more and more disorder, so entropy is always increasing. It's a chemistry joke. If we want to think about the different states of matter and how that affects their entropy or their randomness, right, we can think about both three things: a solid, a liquid, and a gas. Right? if we had a solid, right, and I have, like, let's say I have a solid piece of ice, right, which I'm going to draw there. I've got my ice. All right, if I wanted to go and say I wanted to find one specific atom in that hunk of ice, right, and I found this one atom in the ice, right, that's that little dot there. I got my one atom in the ice. If I came back and it was still ice, I came back, say, in like 10 minutes, right, I could find that atom again by going to the exact same place. Because solids can only vibrate. That's the only movement that they can have, right, is that they're vibrating around, but they're not moving around any other way. Now, if that ice turned into liquid water, right, and I found an atom in the liquid water there, and I came back in, say, 10 minutes to that one, and I wanted to find that one specific atom of water again. Well, if we think about liquids, right, liquids flow, right? They can move around, and actually liquids, not only can they vibrate, but they also can rotate, and they're going to rotate around each other, which is why they flow around. And so if I came back in 10 minutes, that atom would not be in that exact same spot anymore. So the liquid's more random because I can't come back and find that exact same atom in the exact same spot. And then gases, right? If I have a gas molecule, right, it's randomly moving around, bouncing off of things, other gas molecules, off of walls and whatever, right? So if I found a gas molecule, so water vapor, and I came back in 10 minutes and wanted to find it, say, somewhere in the room, well, heck, it could be anywhere in the room because it's been bouncing around for 10 minutes. It's going to be hard for me to find. So that's even more random. So our entropy increases, right, from a solid to a liquid to a gas. And it also, if we're in the same phase, is going to increase, right? And so if I had, say, liquid water, and I increase the temperature of my liquid water, so say from 40 degrees Celsius up to 80 degrees Celsius, right? Well, temperature is increasing, which is increasing the motion of molecules. That's the definition of temperature, is the motion of molecules, right? How they're moving. So if we increase the temperature, then the liquid water, the motion of the molecules is moving a little bit faster, which means that the motion of the molecules is moving a little bit faster. That water molecule that we found earlier is going to be in a different place. It's going to be moving around even faster. It's going to be harder to find, meaning that it's going to be even more random, or there's going to be an increase in our entropy. So here's a pictorial view of us increasing the entropy of something as we increase, first of all, its temperature. So we can see that we have an increase in our entropy as we've got our solid here, right? As we increase the temperature of our solid, right, notice that it is increasing in the entropy, which is shown along the y-axis, right, as we go from 0 degrees Kelvin up to, in this case, somewhere around 190 Kelvin, right? That solid, the randomness is increasing. The entropy is increasing. Then when we melt whatever the substance is, right, that's fusion, right, we're melting it, so we're going from a solid to a liquid. Notice that we have a big gap there in our entropy. We jump up, right, from here up here, so we have a big jump. Then the liquid itself, as we increase the temperature of it, its entropy is also going up, which we can see by this line here. Right, the entropy is increasing because, again, those molecules are moving faster, so they're more and more random. And then we have vaporization, right, which is where we're going to turn our liquid into the gas phase. And we have a big jump there as well in our entropy. And then again, our gas, it's not perfectly seen there, but our gas is going to increase as well. As we increase the temperature of the gas, those molecules are going to be moving around faster and faster, which makes them even more randomized. So here we're going to learn about the third law of thermodynamics, which plays into the previous slide where we were showing, right, that our increasing entropy as we go from 0 degrees Kelvin up to the melting point there. Right, what the third law of thermodynamics tells us is that a completely ordered, all right, pure crystalline solid, right, just means that we have like only one substance in this crystal, at 0 Kelvin has an entropy of 0. All right, well, we should know that 0 Kelvin is a theoretical value that we cannot reach, but if we were able to reach 0 Kelvin, we'd have an entropy of 0. All right, so what does 0 Kelvin means is that, right, remember, temperature is a measurement of the motion or the movement of molecules, well, at 0 Kelvin, we would have no movement of molecules at all. And if our molecules are not moving at all, then the entropy would be 0 because we would know exactly, it would be perfectly ordered. Doesn't matter, it couldn't move at all, it couldn't even vibrate a little tiny bit, so I'd know exactly where that molecule was all the time. That's why we'd have an entropy of 0. Right? Again, this is a theoretical thing that can't happen. So notice that what we're going to find then is that our entropies of our pure substances are always going to have values that are going to be greater than 0 because they can't reach absolute 0, so they can't have an entropy of 0. Thus, they also can't go below that, so they can't have an entropy being negative. So back in Chem 1, back in chapter 6, when we did enthalpies, we saw that we could directly calculate what the enthalpy change was when we produced a substance. Right? I could take some silver, I could react it with chlorine, I could get silver chloride, and I could figure out what the change in enthalpy was by doing that reaction in a lab. We can't do that with entropy. We can't figure out the entropy change of something directly like that. Right? What we actually have to do is we have to figure out a standard value, and then from that we can base everything else off of that. All right? And so, right, what we found on our previous slide is that all of our elements, right, all of our pure elements in their crystalline form have non-zero molar entropies, right? They're always going to be positive values. They can't be 0 because that would be at 0 Kelvin, which is impossible, and they're going to be positive. All right, and so our entropy changes always have to be greater than 0. Their standard molar entropy changes are always going to be positive values. And if we have, though, aqueous things, all right, aqueous things can be negative. So just make sure that you look them up in tables whenever we calculate our entropy changes. Just look them up in case you don't know what the values are. But if we remember back to enthalpies, enthalpies could be 0 for our elements. Here, everything has to be non-zero. So you're not going to come across things that are 0. So make sure that we look those up. So in order for us to calculate the entropy change for reactions, right, and notice that this is delta S, so that's a change in entropy. And notice that we have that not symbol that's there. That means that we are at standard conditions. Standard conditions, which are like 25 degrees Celsius, right? 1 molar, 1 atmosphere. All right, just like when you calculated enthalpy changes, right? If we want to calculate an entropy change, it's products minus reactants. So you don't have anything really new to learn here, right? Just products minus reactants. We're going to look up values in a table and plug them in, right? Remember, these mean the sum of whatever follows it. So we're going to take the sum of all our products minus the sum of all of our reactants. Down at the bottom there are some things in red. It says that the change in entropy at constant temperature can be calculated by these two reactions. All right, those reactions you are never going to see. I'm not going to do any sample problems with it. You're not going to have it on any homework. You're not going to have it on any exams. So don't worry about those ones. Just know that that's something that you might do in like a physical chemistry course. Right, just like when you did our enthalpy changes though, right? Remember that we do need a balanced equation because we need those coefficients. These are in the values for our delta S are going to be in joules per mole, Kelvin. And so we need to know the number of moles of reactants and products, right, for each species because of those units so that they cancel out so that we get delta S in units of joules per Kelvin. We want to get rid of those moles. So just like in enthalpy, we need that balanced equation in order to use that for the coefficients going forward. So once again, in sample problem 20-3, we're going to use, right, our common sense and just us kind of being around in the world to be able to predict whether our entropy change is going to be positive or negative, right? Are we going to be more random or less random, right? More random, positive, less random, negative. So A says a lake freezing. All right, well, we're going from then, say, a liquid water to a solid water. So remember, liquids are more random, so thus the solid has to be less random, and so our delta S is going to be negative, right? We're going to being more ordered or less random. That's a negative delta S. All right, next up I have precipitating lead chloride. So now we're thinking about a chemistry problem. So precipitating lead chloride means that we're taking lead cations and chloride anions, right? They're floating around in water, and now they're precipitating out and they're forming lead to chloride, right? A solid compound. So we're taking aqueous things and turning it into a solid. Well, we're also converting 3 moles of aqueous things into 1 mole of solid. Right? So both of those things should lead us to believe that we're going from these random ions floating around into this precipitate that's now just sitting at the bottom of our beaker. Right? Well, that's more ordered, right? Less random, so our entropy change should be negative. All right, a candle burning is C. Right? Well, this is a combustion reaction because we're burning something. And we're taking our candle wax, which happens to be a liquid. We kind of think of it as a solid, but it's actually a liquid. It flows a little bit. And we're converting that liquid into a gas. All right, well, right, we are taking a liquid and turning that into a gas. So we're going from something, a liquid that's more ordered, to our gas, which is more disordered, right, or more random, which means that we're going to have an increase in our entropy change. So it's going to be positive. All right, and D is weeding a garden. Right, well, if you've got a garden, it's got some weeds in it. As you pull the weeds out, right, you're going to have a much neater, more ordered garden. You're physically having to do some work to do this, right, but it is going to be more ordered, right, and so as we have something that's more ordered, we should have a negative entropy change. So we brought up the units of entropy a little bit earlier, and that for the units of entropy, we're going to look them up, and they are going to be usually written out in joules per mole Kelvin. All right, now they could be in kilojoules per mole Kelvin. Delta H was in kilojoules per mole Kelvin. All right, from Chem 1, delta H was in kilojoules per mole Kelvin. Delta S, usually in joules per mole Kelvin. All right, we're going to want to pay attention to that when we start working the math on these things, because we're going to combine delta H's and delta S's into one equation, and we need those units to agree with each other. All right, so we need kilojoules and joules. We need to convert one of them to kilojoules or one of them into joules. They need to be the same one way or the other. All right, so just pay attention to those things in our calculations when we work those. All right, now, if I look at this, I've got my calcium carbonate there, right? And I can actually calculate the delta S for this, right? So delta S for this reaction is going to be products minus reactants. So we can look up these entropy values, all right? And we can look those up in a table in our appendix. I think it's in Appendix B, pages 5 through 7, which I have a slide that'll tell us that. So our delta S for this, we have, right, our CaO. So we've got, right, 1 mole of our CaO, and I look up the entropy for that, which is 39.8 joules per mole Kelvin. And I'm going to add to that the 1 mole of my carbon dioxide, and I look up its value, which is 213.6 joules per mole Kelvin. And I'm going to subtract off the calcium carbonate, so 1 mole of that times, and it is 92.9. And that's joules per mole Kelvin. I'm just running out of space over there, so I didn't write in the units. And so the delta S for this is positive 160.5. And that's in joules per Kelvin, right? And so notice that it's a positive value, right? This reaction, right, we are going from a solid
and we're producing a solid and a gas. So we are evolving a gas, and that is, right, we're evolving something that is more random. And so this should be a positive value. And notice that it is.
Earlier we discussed the third law of thermodynamics, where if we reach 0 degrees Kelvin, theoretical value, we would have no randomness or an entropy of 0. Right, well, now we're going to learn the second law of thermodynamics, which states that in a spontaneous process, right, there is a net increase in entropy. All right, but that is taking in both the system and the surroundings. If we have the system and the surroundings, we are always going to have a positive delta S. All right, but earlier we learned that, right, a positive delta S only tells us that we're probably going to have a spontaneous process. Right? And the reason that we said that is probably is because that delta S that we're calculating is we can calculate the delta S, right, our entropy change for our system. I can mix chemicals together and I can see how much randomness they incur, right? But we cannot calculate the surroundings. We can't calculate that because, right, if I do an experiment here, right, it might be something as small as me mixing a couple things in a beaker. And I see how much randomness that incurs right there on the beaker. Well, just outside that beaker is part of the surroundings. Well, also Pluto is part of the surroundings too, right? It's impossible for us to figure out how much randomness we caused all throughout the entire surroundings or all throughout the, right, things that are around that system, whether it be really, really close or an inch away or a foot away or a mile away. We cannot calculate those surroundings, so we can't actually calculate that part of it. The only thing we can calculate is the system, but we don't know how that's affecting our surroundings. If we did, then we would know that the entropy change for the universe, if it was positive, would mean that it's spontaneous. But we can only calculate the system. So when it's a positive delta S for the system, it's likely spontaneous, but we don't know it for sure, right? Which is, again, then why we had to come up with a third thing that we're going to calculate, which is called Gibbs free energy. That's what we're going to learn in our next podcast. Is all about Gibbs free energy and then finally being able to know whether a reaction's spontaneous for sure or not.